Heat treatment metallurgy for the heat treater. This is a PowerPoint presentation for HT courses of Mumbai, India. And it's presented to you by David Pye, myself, of Pye Metallurgical International Consulting, located in the United Kingdom. Steel grades. What you will learn. You'll learn briefly how steel is made and a very simple definition of the understanding of the word steel. You'll learn of the alloying elements and their influence on the mechanical and metallurgical properties of the steel. You will learn of the various classifications of steel. You'll further learn of the classification of tool steels. And this will be followed by learning of the classification of stainless steels. You'll learn further the various international steel identification systems. Segment 1. What is steel? Steel is simply an alloy of iron plus very small amounts of carbon. That is a simple definition of steel as one can possibly make. The pioneers of steel making originated in both India and China well over 3,000 years ago. The Western world began to discover the steel developed by India and China when the Europeans began to travel the Great Silk Road from Europe to China via India. Trading allowed the exchange of simple European products in exchange for the iron-based products of both India and China. Steel became one of the first recycling industries with the use of scrap iron to assist in steel making, using scrap iron as a basic ingredient to be added to the iron ore after the iron ore had been smelted to recover the iron. Iron has been used over the centuries in manufacturing weapons, bridges, automobiles, marine transportation, cutlery, surgical instruments, and many other applications. Iron and its conversion into steel has perhaps been the most singular development for industry as a whole during the past 500 years or more. An early method of steel making. Very simply done, they take the iron ore, they heat it up, melt it, to burn off the iron, burn off the oxides and the impurities, and you finish up with the iron, pure iron melting. One of the early steel making techniques that India was famous for was the method of making Wootz steel, which was produced predominantly in the southern regions of India. Wootz steel was well known for its beauty of its surface finish, and of which there's no two pieces of that steel looked alike. In order to make the steel, the ore was first smelted and followed by a melting process in which certain alloying elements were added into the wooded grain to give this type of steel its unique mechanical and metallurgical characteristics. Once we had made the steel, this then required forging, which was done by the master forge, and the forge fire was kept hot by ladies who managed the blowers to blow air into the forge fire. It was followed then by a very special quenching procedure, and India became very well known for this decorative and special type of steel, and particularly when it was used for knives and swords. Two blades. The one on the left is completely different in terms of surface finish and decorative appearance than the one on the right. But you can see how that beautiful pattern covers the surface of the steel. India became very well known for its steelmaking activity, its quality and production development. There are many well-documented illustrations of quality of metallurgy and mechanical properties of the early Indian steelmaking examples. The next two illustrations, they show you examples of the quality of Indian steelmaking. A lot of the students looking at this course, where we're looking at the Delhi pillar. The Delhi pillar is quite unique. It's a cast steel column with a pattern on the surface, and the amazing thing is that no rust appears on the column. A beautiful piece of artistic work. The largest wheeled cast steel cannon. If you look at the size of the barrel in relation to the people standing by the left-hand side of the wheel, you'll see how big that barrel is in reality. That barrel needed a pattern. The pattern had to be made so the iron or steel could be cast around the pattern to produce the gun barrel. Steel classification. A very simple statement that can be made about steel is that steel is grey, therefore everything grey is steel. In other words, we cannot tell the difference simply by observation as to what type of steel we're dealing with. Every country in the world has its own method of grouping steels. The system that has become known to the most universal system has been developed by the American Iron and Steel Institute, known as AISI. The writer, that's myself, shows a tabular form of steel categorization in the first instance, the classifications. On the left-hand side, we have the ferrous materials. That is materials that are made with an iron base. And on the right-hand side, we have the non-ferrous materials. That is materials or metals that are made without the use of iron. On the ferrous side, we can see bottom left on the tree, plain carbon steels. Then we have alloy steels. Then we have tool steels. And in reality, when you think about it, in reality, tool steels are simply alloy steels. Then we have stainless steels. Within each of those groups are numerous types of steels for different purposes. Another classification tree. This once again shows you coming down on the left-hand side down to the ferrous materials and how they're classified. The tree is virtually self-explanatory, and you can see the way or the manner in which everything is grouped. Now we're getting into steels. Steels we have on the left-hand side of the tree, on the topmost illustration, plain carbon steels. The definition of plain carbon steels are those steels without any significant alloying materials other than manganese, sulfur, phosphorus, and that type of element. On the left-hand side of that category, we have low carbon, which are steels up to approximately 0.25 to about 0.3%. Then we have the medium carbon steels, which are again low alloy. The medium carbon steels are once again 0.3 up to 0.5. And then the high carbon steels, low alloy, are those steels above 0.5%. Then we have the alloy steels in the next segment. Same classification where we have low, the medium alloy steels and the high alloy steels. These are steels that are taking alloy materials such as chromium, molybdenum, vanadium, nickel, tungsten, etc. Moving on to just on the center, we have tool steels. Tool steels, once again, we classify those by the W series, and then the W series simply means a water quench. Again, a low alloy tool steel. And then we have the alloy tool steels, which again have higher amounts of alloying elements such as chromium, molybdenum, vanadium, tungsten, etc. Then we have the stainless steels, the austenitics, the ferritics, the precipitation hardening, the martensitic, and I'm showing the pH steels at the end. Below that we have applications on the tool steels. Shock steels, that's the S series. Cold work steels, those are the D series. Mold steels, those are those steels are particularly used for the manufacture of molds, such as plastic molds. Then we have the hot work. Hot work are medium carbon with high alloy up to about 5% chromium, 6% chromium, etc. These are steels that can be used for forging dies, for extrusion dies, shot sleeves, anything which necessitates exposure to heat. The next group, on the sort of next to the end of the classification here, are the high-speed steels. High-speed steels are those steels that are designed to cut other metals, and we have possibly the highest amount of chromium, molybdenum, vanadium, tungsten, cobalt, etc. in those steels. Those are classified by the M series or the T series. Then on the far right hand side, we have the low alloy special steels. Here once again the classification in a little clearer form, where we have left hand side carbon steels, where the carbon steels are low alloy materials, and we have low carbon, medium carbon, high carbon. Then we have the alloy steels, and you could group those under AISI, SAE, then the tool steels, stainless steels, and other steels. Those are the special steels. The plain carbon group of steels. Plain carbon, and this now visually gives you the carbon contents of each of these groups of steels, where low carbon is 0.01 up to 0.3%, medium carbon 0.3 to about 0.5%, and the high carbon 0.5% up to 1%. These are the steels that can be grouped in their alloy classification. Low carbon steels, 0.8% carbon up to 0.29% carbon, and those give you low strength, low hardness values. They're easy to machine and form, and of course they're the least expensive of all the steels. Medium carbon steels, 0.3% carbon up to 0.49% carbon. They're hard and strong after hardening, and obviously more expensive than the low carbon steels. Carbon steels then can be generally classified as steels that rely on carbon as the principal alloy hardening agent. In other words, carbon is the magic ingredient that makes iron into steel and makes the steel become harder. Low alloy tool steels, and these contain 0.55 carbon up to 0.75% carbon. Manganese 0.25 to 0.36. Silicon 0.01% up to 0.32%. Again, a tree formation or description of the alloy steels. Once again, is showing the classifications of the steels. AISI tool steel designations, and these are the tool steels that are based upon the quench medium. Tool steels by quench medium. On the left hand side, on the bottom row, you have the W series. All that W means is a water quench. So really what we have is a medium to high carbon steel with a few alloying elements in there, but only in very small amounts, and that necessitate a rapid cool down such as can be obtained by quenching in water. Then we have the next group in the center, the O series. Same sort of carbon levels, but with much more alloying elements: chromium, molybdenum, vanadium, tungsten. And if you quenched in water, you would crack that steel. So we now designate the steel by quenching, by using the prefix of O for oil and quenching into oil. Then we have the unusual kind of material on the right hand side, which is the air quench steels. No, it's just simply A series designation for tool steels. These are fairly highly alloyed tool steels. And the significance about these tool steels is that once you have austenitized the tool steel, taken it from the furnace, sat it down in a draft-free environment, or you could put a blower onto, an air blower onto the material and blow it cold, and you will find hardness values up to 55 to 62 Rockwell C scale. Classification of tool steels, where we have the tool steels in the center, shock steels at the top, that's the S series, the coldworks tool steels on the right in blue, the special purpose in a brown, the high speed at the bottom in a purple, the mold steels, and then the hot work steels in green. Alloying elements. Iron with carbon is its simple alloying element and will produce, when heat treated, both limited and metallurgical mechanical properties. The approximate maximum hardness that can be achieved by heat treatment in terms of hardness is approximately 62 Rockwell C scale. The influence of carbon in terms of hardness values. The hardness values are on the vertical axis on the left-hand side of the graph. The carbon content is located on the bottom horizontal axis. And you'll notice the higher you go in carbon, up to about 0.8%, the maximum hardness that you're going to accomplish is approximately 62 Rockwell C scale. And you cannot get this plain carbon steel any higher than that. But sometimes it is necessary to get the steel higher in hardness value than, say, 62 Rockwell. In order to accomplish that, we now need to consider alloying elements. The relationship between hardness and other mechanical properties is very limited. The following properties are limited, such as tensile strength, impact strength, torsional strength, yield strength. To improve those mechanical properties, as well as hardness, necessitates finding elements that can be alloyed with the iron and the carbon to improve the desired properties. The groups of alloying elements that can improve the metallurgy and mechanical properties of what we have seen as the plain carbon steels. And it will now be necessary to decide what requirements are necessary and needed from the steel. This illustration shows the different elements that will assist in changing mechanical properties and metallurgy. You have the tree with 3 different groups of alloying elements. Each of these groups will create a different mechanical property and a different metallurgy. The primary alloying elements are then added as ferroalloys such as molybdenum, chromium, tungsten, vanadium, manganese, silicon, and others. Chromium is a very expensive material. Tungsten is a very expensive material. Vanadium is an expensive material. What properties and what alloying elements will do for these materials? Manganese. Manganese is present in all steels, including the alloy steels, as well as tool steels. There's no dividing line between the carbon steels and manganese alloy steels. Generally, manganese is present in amounts above 0.6%. It's also used to reduce the oxide formation. In other words, it's used as a deoxidizer, and it will form with sulfur to reduce embrittlement in the steel. It also assists as a low-cost hardener in some of the lower alloyed tool steels. If it's present with chromium and molybdenum, it will help resist deformation on air hardening, and it's usually found in the A series tool steels. I just want to refer back to the center bullet point where it says to you, it is used to reduce, this is manganese, used to reduce oxide formations and will form with sulfur. There is a particular condition that can arise if you have a high manganese content along with a high sulfur content, and you will form manganese sulfides. The manganese sulfides are a non-metallic condition. So within the body of the material, if the manganese and the sulfur is high or too high, then these two elements will react to form the manganese sulfide, which will give you crack propagation risk. So be very, very careful when you're receiving the steel that has high manganese and high sulfur contents. Carbon. Carbon is the universal hardener in all steels, and it can be found in amounts from 0.1% up to 2.3%. After that, the steels are still steels because they're a mixture of iron and carbon, but we classify those steels that are greater than 2.3% carbon as cast irons. An interesting fact about the steels is that it does not take a significant amount of carbon to affect the hardness of the steel and also the mechanical properties. This element will interact with elements listed below to form carbides. Once the carbon content approaches or even surpasses amounts greater than 1%, it will usually combine with other elements such as chromium, molybdenum, vanadium, tungsten, cobalt, and titanium. Sulfur. Sulfur is considered to be an impurity. and at the primary steel making it is deliberately reduced. However, there are instances when it's necessary to add back the sulfur in very controlled amounts to improve the steel's machinability. Many years ago, lead was added to the steel to improve machinability. The only problem with lead was that as you heat treated it and you exceeded the lead contents melting point, then the lead started to vaporize out of the steel. Sulfur does not have such a problem. Silicon. This material is used primarily as a deoxidizer during the steel making process. However, in large amounts, it will begin to affect the steel's ductility. In the high alloy heat resisting steels, it will assist in the resistance to oxidation at high temperature. Chromium. Chromium is found in a wide range of tool steels and in varying amounts. Chromium is one of the elements that has a tendency to form carbides with carbon in the steel during the heat treatment procedures. Chromium that will assist you in deep hardening, in other words, where you have diameters greater than, say, 25 millimeter. With the high additions of chromium, you can almost get a uniform hardness value in materials slightly greater than 25 millimeter. There's a slight improvement in corrosion resistance. There's also a significant improvement in wear resistance. It can be a disadvantage if the tool steel is held too long at the austenizing temperature by causing grain growth. However, having said that, grain growth will occur as a result of time at temperature. So time and temperature for any steel will affect grain growth. Nickel. Nickel will not form carbides with carbon. The nickel will promote toughness when it's combined with chromium and is added to promote toughness. It will also tend to reduce the steel's hardening temperature and is found in a number of the oil hardening steels rather than in the air hardening steels. It's usually found in quantities around 3% on some of the alloy case hardening steels. If it goes much above 3% on the alloy case hardening steels, there is a tendency for the nickel to initiate the formation of what is known as retained austenite. In other words, a lower hardness value. Tungsten. Tungsten will raise the hardening temperature, that's the austenitizing temperature, and it will form very stable carbides with carbon. It will also inhibit grain growth at elevated temperatures. It's found extensively in high-speed steels, which usually form the excess carbides within the matrix of martensite. Its primary function is to give high red heat hardness. In other words, the tool can start to glow red. In other words, if it starts to glow red, you've exceeded temperatures above 600 degrees centigrade, and the steel will still retain its hardness value. And it's used in both high-speed steels and a number of the hot work steels. Molybdenum. Molybdenum will also form complex carbides with carbides. It will improve deep hardening characteristics of the steel. It's found in tool steels such as hot works, high-speed steels, and usually found in concentrations around 4% plus. It also makes the steel resistant to tempering, and also assists in secondary hardening characteristics of the steel. Vanadium. Vanadium has two primary functions in tool steels. The first one is as a grain refiner and a stabilizer of carbides at high temperatures. It will also have a stabilizing effect on martensite, and this function alone makes it difficult to temper. The cycle times on tempering tend to be longer and require multiple tempering. In other words, one temper is not enough. We have to do a minimum of 2 tempers. Alloy steel categorization. That is the AISI/SAE identification of steels. Once again, we consider how the alloy steels are classified and identified by AISI and SAE. Many countries have different methods of identification of alloy steels and tool steels. AISI have a very simple method of identification which has stood the test of time from the very early 1940s and maybe earlier than that in the 1930s. On the left-hand side of the table that I've presented there, AISI designations. The designations are numeral designations, and for example 1XXX means it's a plain carbon steel. In other words, if you were to see a steel that said 1001, it would mean it is a plain carbon steel, nothing has been done to it, and it has 0.1% carbon. Remember, carbon is the most important thing that we need to know in order to determine the austenitizing temperature. So the last 2 digits are, or 3 digits, are the carbon content. And you'll notice I said 1001, which means plain carbon steel indicated by 1, 0 because nothing has been done to modify it, and 01 means 0.1% carbon. 2XXX, those are the nickel steels, that's iron plus nickel as the principal alloying element with carbon, and it's designated as 2XXX. That means if we see 20XX, it means it's a nickel-based steel or a nickel-bearing steel. Nothing has been done to modify it, and if we had if it was 2X or 2030, what it would mean is 2 being nickel steel, 0 nothing to modify it, and 30 meaning 0.3% carbon, and so on. It is an extremely simple system. Where we get a bit of an anomaly would be under the 6XXX, chrome vanadium steels. On the chrome vanadium steels you can have 6061, you can have it even higher than that, 60100. All that means, it is 6 chromium vanadium steel, 0 nothing has been done to modify it, and 100 means 1% carbon. It's a very, very simple system, very simple indeed. The system's based on a 4 and 5 digit system. The first digit of the system will identify the type of steel that's been identified. As I said earlier, the first digit 1 on a 1XXX identifies the steel as a plain carbon. The second digit will identify any modifications that have been conducted on the steel analysis. The second digit will state if the steel has been resulfurized or rephosphorized. An example of that would be 1,2XX. 1 means it's a plain carbon steel. 2 means it's either been resulfurized or rephosphorized. XX would denote the carbon content. It's the last 2 digits that are really the most important and most informative, as they indicate the carbon content of the steel. The carbon content will determine how we heat treat the steel because of the carbon content. For example, if we see 1201, which means it's a plain carbon steel that's been resulfurized with 0.1% carbon content. Here we have now the tool steel classification and identification in a tabular form. This shows the classification of the tool steels and how the tool steels are identified. The tool steels have taken on the same controlling body, the AISI, and the AISI deemed it appropriate to call the first 3 the quench-based materials, and after that application-based. Quench-based being W, O, and A, water, oil, or air. The next group of steels that we deal with are the tool steels. The first 3 groups are identified by the quench method, followed by high carbon and high chromium steels. This shows the classification, the contents, and other information about those steels. W series equals water hardening. That is medium carbon, low alloy. O series means oil hardening, medium carbon, medium alloy. A series means air hardening, high alloy, requires very careful preheat. S series means it's a shock series steel. It requires oil hardening, has a higher alloy content, and it has medium carbon content. D series. The D series stands for dimensionally stable series. And those are typically oil or interrupted quench from the austenitizing temperature. The high alloy steels classed as dimensionally stable steels. HSS simply means high-speed steels, high alloy, and it's identified either by a T prefix, or which means tungsten as the principal alloying element, or M, which typifies molybdenum. Although the tool steels contain high alloy content, they're still alloy steels, but are classified into in a different and separate manner to the alloy steels. The tool steel, because of the high alloy content, requires very careful heat treatment, particularly with the quenching procedure. Some tool steels will require interrupted quenching methods. Some will require vacuum heat treatment because of surface oxidation. Some will require atmosphere treatment, and this is to protect the steel against decarburization. Carburizing steels. Carburizing steels will require atmosphere heat treatment. Some carburizing steels will require low pressure carburizing, LPC, to protect the steel carburized surface against grain boundary oxidation, GBO, sometimes known as the intergranular oxidation, or IGO. Another feature of the carburizing steels is that they're all low carbon steels. Again, showing the carburizing steels. Steels that are classed as carburizing steels are generally all low carbon steels. And you can see the classification there with the dark red in the center for the carburizing steels, low plane carbon, which is in the green, the dark blue, low carbon, high alloy, and on the light blue, low carbon and low alloy. Here are some of the popular carburizing steels. AISI 9310, 8620, 8720. A number of these steels, particularly the 9310, 8620, 8720, 8617, are typically used in the aerospace industry as well as the automotive industry. Typical nitriding steels. AISI 4140 was originally designed and developed as a nitriding steel. So AISI 4140 will nitride quite nicely. Remember, and not everyone recognizes this, the number of alloying elements contained in a nitriding steel, particularly those that will interact with nitrogen, will form stable nitrides. But the one element that everyone overlooks is iron itself. Iron itself has an interaction with nitrogen at temperatures to form iron nitrides. The difference between iron nitrides and, for example, a chromium nitride is that the iron nitride is soft. So what does this mean? It means that a plain carbon steel can be successfully nitrided. But you might turn around and say, yes, but we can't get the hardness we can get with an alloy steel. That is true. But what you must remember is that you have improved the surface hardness. You've taken it up to a hardness value of somewhere around 44 Rockwell C scale, but you've also given it another advantage, and it is that of corrosion resistance. It won't stop corrosion, but it will minimize corrosion. So iron is a typical nitride former. The nitralloy steels, those were developed in the early 1900s. Nitralloy itself, the Nitralloy M, Nitralloy 135, those steels were developed as nitriding steels in Europe and later in the United Kingdom with Thomas Firth and John Brown Steel Company. The British standards BS 970A is EN40 A, B or C, and that is a nitriding steel. BS 970A EN41 A or B, that means EN41 has had aluminum added to it. Aluminum is perhaps the strongest nitride former that there is. H series, those can nitride successfully. H10, H11, H13. The H10 and H11 are very low on the totem pole, if you will, for high surface hardenability, simply because they have not got the same chromium alloying element as one would find with H13, H19, H21. High-speed steels, these will nitride beautifully. M series and the T series. Stainless steels, austenitics, ferritics, martensitics, pH steels, and the exotic steels. Remember, in the stainless steels, there is a significant amount of chromium. Chromium is a strong nitride former. So it doesn't matter whether it's an austenitic or a martensitic, it will nitride. The difference being is that the austenitic will not have a good high hardenability in the core to support the case. We've now reached the end of this session. The range of steels and cast irons. Cast irons are also another subject, is wide and varied. This ranges from basic steel making to the advanced steel making techniques of vacuum degassing, electroslag refining, which are steel making techniques for exceptionally clean steels. Once you can begin to memorize the various steel classifications, the analysis knowledge is comparatively easy, as it is the chemistry that is really important to the heat treater. In conclusion, final conclusion, I give you thanks to you, the student, for taking the time and effort to participate in this presentation, and more importantly to the staff and management of HT courses in Mumbai, India, for their vision and foresight for presenting these courses for you. I myself, David, I give you sincere thanks, and all that remains now is for you to take the 20 question test for your certificate. Thank you sincerely. Bye-bye, David.